All right. Good morning, students, faculty, professionals, and distinguished guests. My name is Giovanni Zarur, and I'm the Vice President of Blockchain SC. I'd like to welcome you all to Day 2 of the second inaugural VanEck Southern California Blockchain Conference, co-hosted by Blockchain SC and the USC Marshall VanEck Digital Assets Initiative. Yesterday was definitely an electric start to SCBC with fantastic headliners including Imad Mostak, Chris Dixon, and Anatoly Yakovenko. Today, we're excited to see you again for a stellar lineup of keynote speakers accumulated by Blockchain SC team. I'd like to thank the guest speakers for making the effort to be here today. It wasn't possible without them. Thank you for our conference sponsors, VanEck, EduDAO, Gauntlet, Ava Labs, and Pluto LA for making this idea come to life yet again. Finally, a huge thank you to our co-hosts, the USC Marshall School of Business and its VanEck Digital Assets Initiative, also known as VEDA, and especially Eric Chung, the director of VEDA. When Professor Anthony Borquez, the co-director of VEDA at UC Marshall, first came to us in September 2022 with the idea of a grand blockchain event at USC, we never would have thought that would culminate to this. In November 2022, Blockchain SC and USC Marshall hosted the first SCBC just 1 week after the crash of FTX, and a series of very, very unfortunate events in the crypto space. Most people here will remember that year. Even at the spur of a painful bear market and a life-threatening time for the industry, we put on one of the best events in Southern California for over 1,000 attendees. Having survived through all of that, we now find ourselves in a time of excitement and renewed confidence in the future possibilities of crypto and blockchain technology. If you stay put as an enthusiast, builder, academic, or student in the blockchain space, congratulations. Maybe it's our delusion, maybe it's our conviction, but we're still here. One of the great things about Web3 is its lack of barriers. Thus, mere university students from UC Berkeley to USC and Stanford and Penn have contributed an incredible amount to this industry. There's no shortage of college graduates from the top university blockchain organizations that have built revolutionary innovations in the space. I'm glad to say that USC has become one of those ecosystems. I've seen Blockchain SC grow and flourish. In just 6 years, the organization morphed from an evening blockchain discussion group into a very legitimate student organization, well known on campus for having some of the brightest minds building the future of the technology. Blockchain SC boasts alumni including successful startup founders, professionals working at top Web3 companies, researchers, engineers, VCs, and everything else in between. Currently, Blockchain SC maintains governance, research, and engineering teams consisting of students from all majors at all university levels. In our partnership with A16Z Crypto, we've become one of the largest and most active governance delegates within the Optimism ecosystem, with additional protocol involvements in the works. We've been contributors to many public goods funding programs, helped decentralize protocols, build software, and publish open-sourced research in an open-source, democratic, and on-chain manner. In the past, we've maintained many partnerships ranging from VC firms to alumni-founded companies. Students at Blockchain SC attend conferences every year and place in top positions at hackathons all over the world. It may sound like I'm boasting, but we really are all that. Source, trust me, bro. Anyways, I hope the remainder of SCBC number 2 exemplifies the great thing that we have going on here. Blockchain SC is a pillar of innovation and talent in Web3, and we hope it continues to be after we pass on the torch. I hope you enjoy the talks and networking sessions we have today and take some inspiration, learning, or new connections home with you. Most importantly of all, however, I hope you don't miss out on our exclusive Beverly Hills Mansion after party tonight. All jokes aside, thank you and enjoy Day 2 of the 2024 VanEck Southern California Blockchain Conference. Thank you.
Hello everybody, my name is Luca Cordova-Stewart, and it's my pleasure to announce today's first speaker. Tarun Chitra is the co-founder and CEO of Gauntlet, a simulation platform for crypto networks. Gauntlet helps developers understand how decisions about security, governance, and consensus mechanisms are likely to affect network activity and asset value. He fell into the space in 2011 while working on ASICs at the D.E. Shaw Research as a scientific programmer, observing the rise in Bitcoin mining rigs. A true OG. His research includes over 30 papers on crypto, including the highest cited paper within DeFi. Previously, he worked in high-frequency trading for Vedic Labs. He holds a BA and a BS from Cornell University. Please join me in welcoming Tarun Chitra.
Thanks. Thanks, everyone. I was trying to figure out whether to do a sort of more technical talk or less technical talk. So somehow this talk is exactly in the middle. So hopefully it's not too crazy. But one kind of very important unifying theme across a lot of things within crypto is, what is the notion of the principal agent problem from traditional finance or sort of traditional mechanism design within this world? And in a permissionless world, principal agent problems are actually much more difficult to reason about. For instance, one actor can be a principal in one round of a game, and then they can convert to another actor in another round of the game. And this type of collusion makes these systems a lot harder to kind of design. So we're going to kind of talk through what that looks like. So, first, give a little background on DeFi, decentralized finance. I know many of you might already know a lot, but hopefully this will give us a common sort of vernacular. And then we'll talk a little bit about what principal agent problems are and where they show up. The second thing we'll do is talk a little bit about mechanism design within DeFi, how it's sort of different from mechanism design in traditional finance, and then sort of give some examples and talk about open problems. So again, this is meant to be sort of somewhere in the non-technical but talking about technical things realm. So for people who wanted either one side or the other, apologies in advance. All right, so blockchains and DeFi. So when you think about a blockchain, the simplest way to describe it is sequential ledger of economic transactions. And the idea is that a network of participants, known as validators, uphold algorithmic covenants that are specified within software. In order to incentivize these parties to not collude, there need to be sort of sufficient incentives provided. And different types of users should not be able to cause penalties to one another in sort of an unfair manner. And the key thing about public blockchains is this notion of permissionlessness. So you need incentives to ensure there's Sybil resistance, which means that I can't split my assets and pretend to be multiple agents and get a higher reward. But I also need to sort of have some notion of commitment of collateral. So the collateral varies from network to network. Proof of work, of course, the collateral is energy or hardware. In proof of stake, it's sort of a digital asset that hopefully has sufficient liquidity or price behavior. So, that's sort of the TLDR. I think a lot of you probably already know that. I think the more interesting thing is to think about how the supply chain of transactions in the blockchain works. So first, you start with sort of non-strategic users. So this is a user who says, hey, I want to buy a dog whiff hat right now at some price. I don't really care what the price is. I don't want to get ripped off, but I just don't care that much. And this user has a wallet. A wallet is sort of specified by a cryptographic identifier, public-private key pair, could be a threshold signature, lots of other things, identity-based encryption. And then there's strategic users. Strategic users try to earn excess returns by bundling non-strategic user transactions and then adding or removing or reordering those transactions into some group. These bundles are submitted to block builders who try to build a whole block, a sort of batch of transactions to be confirmed. And those builders bid in an auction for getting their block included with a validator who is chosen by the protocol. So what you see here is this idea of going from less strategic users to more strategic users to sort of randomly chosen users. And so from this you can already see the notion of a principal, someone with capital trying to get a transaction done, like the non-strategic user, has to interact with many agents along the way. Decentralized finance is a way of sort of using smart contracts to facilitate these types of transactions across many different types of participants. So as you could see just from the basic transaction flow, there's many different participants that take place in the life cycle of a blockchain transaction. Decentralized finance protocols effectively have covenants, payments, and penalties enforced via smart contract rules. And the key thing about permissionless networks is that anyone can participate. Anyone can provide liquidity to some of these markets. Anyone can be a borrower, provided they meet the algorithmic covenants. And the most popular markets are automated market makers, lending, and perpetual futures. So a natural question you might ask is, well, this seems harder. You have to convince many different parties to coordinatively work together to generate a transaction that maybe would have been simpler if I had a single entity. And a couple of the main benefits of DeFi versus traditional finance are, firstly, you get the same quality of service regardless of where or who you are. As long as you're a cryptographic address that meets a bunch of covenants, e.g. you have a certain amount of assets or you've participated in a certain sequence of transactions in the past, the protocol will give you the same service, and you can see that. And that's sort of a very different kind of world than the current credit-based economy. The second thing, which I like to think of as, like maybe the 2010s were the era of sort of user-generated content being financialized. The 2020s in crypto is more of what I would call user-generated finance. So users can write a small amount of code, they can use a small amount of services to generate sort of arbitrary payoffs. And these payoffs, in the normal economy would require hundreds of legal contracts. They would require different types of settlement, potentially multi-jurisdictional settlement, versus settlement on a blockchain is I can compute something like these formulas and give you this payoff, and sort of everyone can agree that the payoffs were done correctly without needing a lot of manual intervention. Okay, so now we get to the main question about principal agent problems. So, obviously in much of finance, principal agent problems have been the source of a lot of historical losses. The financial crisis was sort of a great example of times when the incentives of the agents doing actions on behalf of principals were not particularly well aligned. So what is the principal agent problem? So we can think of a principal, so someone with capital, maybe it's a user with $5, maybe it's an endowment with $5 billion, that has a value for what happens if they take certain actions with their assets. So maybe they invest in a fund, maybe they build a new building, maybe they sell existing assets. There's a bunch of different actions they could take. But the principal doesn't know the set of all actions. So think of a university endowment. They don't know the set of all investments they could make, but they do want to get those returns from those investments via actions they don't know how to take. So what they do is they try to maximize their value, at least expected value, by offering an incentive to managers, who are the agents, who invest on their behalf. And the incentive is meant to try to be aligned. So maybe it's you get paid based on the performance of your asset allocation, or you get paid based on sort of different types of performance metrics. In this case, in the traditional finance world, when I think of, say, a college endowment and a fund manager of a hedge fund or venture fund or private equity fund, it's much clearer who the principal and the agent are. The principal is the endowment, the agents are the fund managers, and it's very unlikely that they're both the same entity. But in the permissionless blockchain world, that's not true, because sometimes someone who's a principal could also be an agent on the other side, or vice versa. In this network of validators, anyone can sort of act as an agent to manipulate. And so this sort of means that it's very hard to control what the correct incentives or the types of users are. And when I say types there, I mean it in the sort of economic sense. So what are these kind of unique features of DeFi? Well, first off, there's many principals and many agents. So if I think about an automated market maker like Uniswap, there's many people pooling their assets into a liquidity pool, and all of those people are agents who are serving the different swappers. At the same time, within a block, there's many swaps, so there's also many principals, many users trying to interact. And this means that the mechanism design has to sort of deal with the idea that the types of agents who are participating might be unknown and be changing over time, and that the numbers of these agents can change and fluctuate arbitrarily. The impressive part about blockchains is that they generally make the cost of entry and exit into a market low, but that also means there's a lot of, the cost of collusion is actually lower in a lot of scenarios. And so this kind of makes the economics significantly more complicated, and figuring out the sort of optimal payments between users can be hard in a sort of formal complexity sense. Okay, so now we kind of have the background of what a blockchain is, what DeFi is, and where principal agent problems show up within this setting. So now we'll try to make this a little more formal. So permissionless mechanisms can sort of be thought of as these feedback systems that have a few parameters. The first is a set of agent types. And concretely, a set of types is sort of a set of utility functions and a set of policies that you sort of kind of execute based on those utility functions for agents who are trying to earn fees from principals. There's now a set of principal types, which is the set of types of users who are trying to earn income on their capital but are outsourcing it to the agents. So an example, again, of a concrete example is, say you own a bunch of Ethereum. You don't want to run a node to stake it. You might delegate to a node operator like Coinbase or Lido. And Coinbase or Lido are acting as an agent for you, and we'll talk a little bit about that example later. One very important distinction between classical mechanism design is that the action space between the principals and the agents is joint. So if I'm a principal, and maybe, say an agent goes and puts my funds into a liquidity pool, and suddenly that liquidity pool is about to have a liquidation or some type of adverse event, I can go liquidate my own capital and avoid the loss. This is something that in normal finance couldn't happen. I couldn't suddenly take the other side of the market very easily. And more formal definitions of you need value functions that sort of depend on the types of all users. They're kind of not isolated. And roughly speaking, and I won't go into too much detail about this, but you can think of this kind of picture that's drawn here as representing this feedback loop of how these kind of systems evolve in terms of their reward mechanisms. So what are some properties one might want out of these permissionless mechanisms? So the first property, which is something that in the traditional world actually tends to matter a lot less, is a property that sort of economists call credibility. And so credibility is this idea that a seller cannot deviate, cannot add, a seller of an item doesn't have strategies that can basically cause losses to buyers by them faking being a buyer. And so that sounds a little complicated, so maybe I'll give an explicit example. So suppose you have a seller who wants to sell a single item in an auction, and you have a bunch of bidders bidding on the auction. Let's consider two different types of auctions, which are sort of illustrated here. The first is a first price auction. So whoever bids the highest value, they get the item and they pay what they bid. So say bidder 1 bids $5, bidder 2 bids $10, bidder 2 gets the item for $10. One thing that people sort of know is that those types of auctions have a lot of collusion. If bidder 1 and 2 say, hey, look, we both think this thing is worth $12, but we both agree that neither of us will bid above 10, then they sort of cause a loss to the seller of $2. And the reason for that is they're not bidding their true value. In a second price auction, say we have the same bidders, one bidding 5, one bidding 10. the one who bids 10 pays what the other one, the second highest price is. So they would bid 5 in that case. And one can show that this makes this auction truthful. The problem is if the seller, who you can think of as an agent, and the bidders, who you can think of as principals, collude in the sense that the seller makes a bunch of fake bidders and adds in a bunch of bids at $9.99, they'll degrade the second price auction back to the first price auction. And so in a permissionless world, you can't really stop the seller from pretending to be a buyer, right? That's the censorship resistance piece and the idea that anyone can create a new address and join. And so you have to actually design these mechanisms to have these types of credibility properties more directly in a way that in the centralized world, in like a Google ad auction, you don't have to do. The second thing you care about is this notion of collusion resistance. I think credibility gives you one notion of this, but there's a notion in which certain types of agents can collude, in the transaction lifecycle process I showed earlier. Some of the more strategic agents could collude to make the cost to the non-strategic agent a lot higher. And you effectively want to make that cost of collusion quite high when designing these systems. And the final thing is incentive compatibility, which is sort of, hey, look, these agents also need to be able to make money, otherwise they won't be there, and then the system won't work. So you have to have both sides of the market kind of happy. One important thing to think about is that when you naively try to write out permissionless mechanisms, you'll find that you run into a million impossibility theorems. And one of the reasons for that is that these types of collusion things are very, if you have a really computationally unbounded actor, it's very hard to reason about whether the system is safe or not. And so one really important thing that permissionless mechanisms have to have are constraints in terms of commitments that are made. Those commitments can be economic, forcing users to post collateral. Those commitments can be cryptographic, forcing people to post a zero-knowledge proof of something. But the real important piece is that why do we need cryptography in these types of permissionless mechanisms? One argument for it is that you use the cryptography to limit what actions certain actors can take. So you can use it to limit collusion amongst certain agents. You can use it to limit particular types of actions that can be taken. And so one necessary facet of any mechanism that has worked on-chain in the last 5 years is that it employs some form of computational bound on the agents. This inevitably leads to sort of a set of emergent phenomena within these systems. These emergent phenomena include things that you don't normally see in normal finance, like maximal extractable value. So there's been a lot written about this, but this is things like permissionless front running, sandwich attacks, forced liquidations, oracle manipulation. These types of things come from the strategic agents being able to collude ahead of the non-strategic agents. And the second thing is, in a multi-chain blockchain world, the fact that different blockchains have slightly different rules can sort of allow people to take advantage of those types of things. Okay, so let's recap where we are. So first, we talked about blockchains, DeFi, and principal agent problems. Then we talked about how you think about mechanism design from an economic perspective in this permissionless world. What are the features that are completely different to the centralized world? And now let's try to be a little more concrete and have some examples. So the most simple example is proof of stake. Maybe it's not actually the most simple example, but it's got to be the most well-known example. And as mentioned, proof of stake sort of relies on having this network of actors known as validators who lock collateral. They put up a resource in order to generate valid transactions. And so they come to consensus on what a valid transaction is, and then anyone can verify that it was valid afterwards. There are a bunch of different participants who kind of can sometimes be proposers or principals and agents. There's a proposer who is a validator who has won the right to produce a certain block at block height h. And that validator runs an auction to pick a block. There's a block builder who bids in this auction to get their block in. which might have order flow or transactions that benefit them. And there's finally strategic users. Now, you could very easily imagine that proposers and block builders are the same entity. And in fact, in practice, we've found that what's happened in Ethereum since October 2022, is that there has been a lot of vertical integration between these two agents, which is effectively the same as them colluding. And what's interesting is that this sort of means that when you're designing these systems, you have to assume these agents can collude. And I think one of the main sort of mechanism design problems within Ethereum right now, and Solana actually as of the last few weeks, is really figuring out how to make this system incentive compatible. So won't go into too many exact details here, but I try to give you some idea of like what this would look like symbolically, where you have a definition of the principles, you have a definition of the agents, and you have a definition of the set of action spaces, and sort of like what kind of value functions they have. And the point for writing this is not that, hey, like you should take away that, like, hey, this is giving you some really clear formula for how to think about this. But it's the idea that you can decompose this kind of complicated system of many actors into these kind of simple building blocks and then write out the sort of equations. Like that's more the thing that's interesting. So what are the principal agent problems specifically that people want to solve? The first is sort of, how do you optimize dynamic fees? So, in Ethereum and Solana, well, Solana not yet, but Ethereum, Avalanche, and Near, there already exist dynamic fees. So dynamic fees, think about like surge pricing when you take an Uber. The question is, how do you choose dynamic fees that benefit both sides, the validators who are earning the fees, as well as the users who are using the fees to say how much they want their transaction included? And you want to sort of optimize the welfare of both parties. And there's been a lot of work on this, some on impossibility theorems, some on fee optimization, so that's sort of type of paper that I worked on. The second thing is there's collusion between principles, and this is liquid staking tokens and staking derivatives, where effectively large pools of operators collude to kind of say, hey, look, we have the highest stake, we'll give you the lowest variance return on your capital. In this case, you have a lot of very interesting principal agent problems. For instance, the stake concentrates. In Ethereum, Lido has 33% stake. In Solana, Jito has like 60-something% stake in the staking derivative. And so there's a natural notion of collusion between principles. And finally, MEV is sort of this example of collusion between principles and certain types of agents. The next type of thing that, again, think of this more schematically is like we can write out this set of principles, we can write out the set of agents in automated market makers. So automated market makers are these smart contracts for people who want to earn yield on their assets to deposit, and people who want to trade against those assets to go from one asset to another to be able to be matched. And as you can see, there's actually quite a few different types of agents. Sometimes they interact with each other and change form. And here the sort of principal agent problems are how to minimize arbitrage loss while still facilitating transactions, how to avoid losing fees to strategic users, and how one should think about aggregating orders within these systems. And finally, leverage protocols. These protocols have one side of the market that's a lender, one side that's a borrower, one side that's sort of arbitrageurs of some form or another. And these types of markets do require sort of thinking about whether the principals and agents collude or not. And here sort of the problems are things like optimizing interest rate curves to the benefit of both sides, which is a much more difficult problem than meets the eye. Oracle manipulation, this is sort of the one that, I think the principal agent collusion has had the highest losses to users, and then strategic borrowers. So these are sort of just kind of high-level facets about some of these phenomena that come from when you think about these as principal agent problems, you can sort of find surprising results. Like sometimes some of these collusion things are beneficial to the user. Sometimes it turns out you have impossibility results, like you can never get these things to be collusion resistant. And sometimes you may trade off things like efficiency for censorship resistance, and you can't get both. Cool. So the final thing I am going to leave you with is sort of what are open problems in kind of this world. The first one is this, again, this idea of credibility, where one side of the market can impersonate the other side and make losses for other types of users. Is there a way to do that generically? The second is sort of thinking about things in terms of contracts between these principals and agents. What can be learned from what we know about contract theory to what people are doing on chain? Do they look the same? And finally, capital efficiency. A lot of the mechanisms on chain require a lot of collateral from the users to be made safe in a permissionless environment. Figuring out these precise relationships between principals and agents is effectively the way to reduce collateral requirements and make these decentralized systems hopefully much closer to the efficiency capital-wise of centralized systems. And obviously there are going to be some types of lower bounds to these types of things, and I think that's a theoretical problem of interest. So the TLDR, most problems in DeFi can really be viewed as multiple principal, multiple agent problems. This is kind of an area that people in economics kind of avoid because it's annoying and ugly, but I think you're sort of forced to think about that in these systems. And really understanding the types of conditions that are important in these settings is important to designing these protocols more efficiently. And I guess this is what Dolly's interpretation of principal agent problem is. Doesn't really say much. But that, thanks. I am not sure if this is questions or do yeah, up to you.
Just deeply curious about how you and Gauntlet are engaging the market, who you're working with, and how you're helping to solve some of these problems.
Yeah, so what we do is we spend a lot of time building models of simulations of these different agents interacting with protocols and saying, hey, actually this type of collateral requirement, like this type of margin requirement is actually too high, so maybe you should lower it so that it's better for certain types of users. Or actually the market is really volatile, there's no liquidity, actually you should increase the kind of margin requirement. So a lot of what we do is effectively solving these types of problems, but in a domain-specific way of like, hey, a lending protocol needs to figure out what these parameters should be, and those parameters depend on market conditions that are on-chain and market conditions that are off-chain. So liquidity conditions on Binance, liquidity conditions on other venues, spot and derivative venues. And so this is sort of a culmination of me trying to abstract and generalize a lot of what we did to this setting of, hey, actually, a lot of these kind of problems and things when you want to compare efficiency in centralized systems versus decentralized systems boil down to really understanding the relationships between the participants and analyzing how their behaviors change in this world. The cool part about blockchains is that I can go look at the actual actions that all these participants are making on chain and then fit some sort of model of that and then see how well it predicts what happens in the future. In normal finance, that data is not very public. So it's very hard to actually do that efficiently. You might only have one side of the market's data and you have to guess what everyone else is doing. But the on-chain markets actually do tell you most of that. And so that's why it's actually an interesting place to study this sort of multi-principal, multi-agent type of thing, which in reinforcement learning and machine learning and in economics is not popular because, again, people don't have a very good data set that's trained for doing it, whereas here you do. And then that's sort of what we work on for specific use cases.
And then the use cases, so that's for protocols or for hedge funds?
It's for protocols to optimize sort of fees they're charging, fees they're earning, so like revenue for the protocol, while also B, making users able to use it. So it's sort of marketplace optimization, which in a lot of centralized entities that exists, right? Like Uber does a ton of marketplace optimization. We just do it for these protocols.
Hey, so my name's Robert with the Inclusive Design Institute, and I've got a specific question regarding the collateralization. So, do you know of any research or methods to make that more accessible? Permissionless finance and permissionless network by default is more inclusive and more accessible to more people, but then we have this concentration of influence that exists within collateral. Is there anything that you're aware of to help share that out and decentralize the holders of that collateral?
Yeah, so it's a good question. So this idea that you have these collateral requirements in a permissionless world are basically because these sort of principals and agents could collude to abscond with, say, fees or let's take a more simple example. Like I have a lending protocol. There's a lender who puts up capital. There's someone who borrows that capital. If the borrower wasn't over collateralized in a permissionless environment, there's really no recourse they have. You can't take them to court. You can't do anything. And so the recourse with collateral is, well, the protocol can seize your collateral and sell it, right? Now, there is a sense in which, for some protocols, cryptographic guarantees allow you to lower your collateral requirements. So if I can prove some properties, let's say I have some assets on a rollup like Optimism or Arbitrum, and you're on Solana, and you are a lender, and you want to give me a loan. Now, I could bridge my assets from Arbitrum and Optimism and pay fees to move my assets over. Or you could imagine a world where I could generate a ZK proof or do some type of MPC type of thing, and I can prove to you I have assets somewhere else, so you can give me the loan, and I give you some form of a way of collecting on it. There's a sense in which these cryptographic guarantees can lower collateral requirements. They can't lower them arbitrarily, but a lot of that type of design space is what I think people are exploring, of like using cryptographic guarantees to lower the requirement. Now, there's obviously going to be, in a permissionless world, some limits. You're never going to be as good as the centralized world. But I think, people are kind of working on this kind of efficiency problem, and a lot of it comes down to figuring out when particular parties can collude and can't collude.
Hey, Tarun, thanks for coming. Quick question. As I'm building this futarchy, how would I, any suggestion for building a principal agent framework to fit it into a futarchy kind of system?
Yeah, for sure. I think usually in futarchic systems for a DAO, the DAO is the principal and the agents are the market participants. One important thing to think about, which is actually very important, is like, how do you guarantee that there is sufficient liquidity for the agents to participate and in a truthful manner? And thinking about ways in which the DAO uses its assets as sort of liquidity or collateral for users to place bets on what governance decisions should be taken is sort of the main thing you have to think about. And I think there is a sort of weird sense in which futarchy systems which are sort of prediction markets for DAO governance. Sorry, I should have given some background. So these systems are basically, say I have a DAO, let's say it has, $100 million, and there's three things a DAO can do. One is like fund a building at USC. One is donate to a charity, and one is buy dog with hat with all the money. And a DAO, voting in governance systems is generally kind of hard. It's hard to get people to participate in the long run. It's hard to get people to have incentives. But one thing you could have is a DAO basically says, hey, we're going to have a prediction market where people can bet on the three outcomes, and whichever outcome happens, you get rewarded. And so there's a sense in which these markets are sort of like governance via prediction market. The hard part about them is you could manipulate those outcomes, right? Like if there's not much liquidity to trade the yes or no on the buy dog with hat, the dog with hat DAO can go buy up all of your DAO's tokens and say like, spend all the money on dog with hat. And so I think making these things non-manipulable needs some notion of this collateral safety. And yeah, you should think of it more like a lending protocol in that sense.
So regarding lending protocols, you mentioned the interest rate problem, like how to optimize interest rates for borrowers and lenders. I'm just curious, like, how do you think about that kind of parameterization at Gauntlet? And then how do you think is the best way for protocols to do this, to decide on the interest rate? Because like whoever's deciding is like creates the principal agent risk.
Yeah, so there's a few weird problems in interest rate curves that I think are sometimes subtle and people are worth thinking about. So let's suppose I have I know perfectly all the future demand of this lending protocol, and I could fit an interest rate curve that is exactly the matches supply and demand perfectly, with no excess at 100% utilization. That would maximize fees for the lenders. That would also maximize the amount of capital the borrowers could have. The problem is, if I had such a thing and the curve that's used is complex, you've created a bunch of MEV because now it's much easier to actually front run all of the borrow and lend transactions when the curve is actually more complicated. It's sort of like an AMM that has a complicated curve tends to have a lot more like issues for LPs it's harder for them to figure out how to allocate. You have the same problem of the clearing price to find for the supply and demand is much harder because there's these active MEV agents who can reorder and like cause you to get a worse interest rate. So the first thing is you want the curves to be as simple as possible, and less because there is this kind of these other agents can interact and make the pricing worse. The second thing is some notion of risk-adjusted yield of like what is your target utilization? How much capital do you want to keep on hand for people who are withdrawing from the protocol to be able to withdraw at any time versus not maximizing yield, right? So like if I have a protocol that's at 100% utilization at all times, that's great for the lenders until there's a liquidation because now they're taking the losses immediately, right? So there's this trade-off between capital utilization and sort of risk, and picking a target utilization is effectively picking a risk level. And all these other parameters around that, such as like reserve factors, such as like insurance fund size, those are meant to kind of allow you to have a higher target utilization on average. But you have to keep in mind things like what's the volatility of the interest rate in terms of volatility of borrower demand. And so there's a lot of features like that go into this. It's sort of like more complicated than I think I had thought 4 years ago, whatever, 5 years ago.
Should it be set by a DAO or Gauntlet or by AI?
I mean, I would love for it to be the last one, but I think the problem with most of the on-chain AI type of stuff is it creates a lot of MEV. You can you deterministically know what the change is, and you can run the same model, see what the change is, and front run the transaction. So you actually really do need some sort of private commitment type of thing. You need a TE or you need ZK. I don't think you can get away with DeFi parameters from fully open AI models right now. Cool, thanks.